Hi everyone! In this video, we'll be introducing the concept of logarithmic differentiation, which is a useful strategy for calculating certain types of derivatives. This method is motivated by reminding ourselves of some useful things that logarithms can do. We see here one of our familiar laws of logarithms, and although it's an informal way of putting it, this law essentially says that logarithms can turn multiplication into addition. In similar fashion, we have another law that says logarithms can turn division into subtraction, and yet another law that says logarithms can turn exponents into coefficients. If you take all three of these statements together, you might say that logarithms turn things that are hard into things that are easy, especially from the point of view of finding derivatives. In particular, it turns out that applying a logarithm before taking a derivative can be a good idea, since it might help us avoid annoying steps such as product and quotient rules. Consider this function, for example. If you wanted to differentiate this, you'd need to use the quotient rule, product rule, and chain rule several times, which would get pretty tedious. So I'm proposing that we try avoiding those rules entirely by applying a logarithm before we start taking the derivative. So starting with the function that we've been given, let's apply a logarithm, making sure to do so to both sides. Technically, you could use a logarithm with any base you want, but the natural logarithm tends to be the easiest one to work with when it comes to taking derivatives, so that's the one that's typically used. Now, the entire reason we applied a logarithm is so that we can use logarithm laws to change multiplication and division into addition and subtraction. So you can pause and check that those laws would provide us with this result, but that's not all we can do, because for the purpose of finding a derivative, it would be even easier if we turned our exponents into coefficients, starting with this first term. In the second term, the square root can be viewed as an exponent of 1/2, which can also be pulled out in front. And for the third term, that exponent of 6 can be pulled out front as well. And now that we've applied as many log rules as possible, we're ready to take our derivative, but we must do so implicitly, since on the left side, the variable y is contained inside a logarithm. So the y is not by itself, we gotta differentiate implicitly, which is no problem. We know that on the left side, the derivative of ln y is 1 over y times the derivative of y according to the chain rule. On the right side, the derivative of ln x is 1 over x. And for the next term, the derivative of ln of something is 1 over the something multiplied by the derivative of that something, again using the chain rule. The same approach can also be used for differentiating the last term. Now, the goal here is to figure out what dy over dx is equal to, but now we're set up to figure that out. All we need to do is multiply both sides by y to get that dy over dx by itself. So the entire right-hand side gets multiplied by y, and we may as well do some cleanup at this stage as well. I made a few simplifications there to the right-hand side that you can pause and check if you like. Having come this far, we've found dy over dx, which is what we wanted. Although it would be better if this were expressed fully in terms of x, and we know what y is equal to after all, so we may as well insert that formula where we see y and present this as our final answer. Reflecting back on all the steps that led us here, you can see that we did completely avoid the product and quotient rule, with the trade-off being that there was just a bit more setup to do at the beginning. But you could imagine that for a function that contained, say, 100 different products and quotients, that price would be well worth it. For future reference, logarithmic differentiation is the name given to this technique of applying a logarithm to both sides and then differentiating implicitly. There's one little issue I swept under the carpet here, and that's the fact that we can't take the log of a negative number. So we should be careful, especially when we're applying logarithms to expressions which contain variables, since we if there's variables involved, we don't really know whether the expression might represent a negative value. So for that reason, it's common to take an absolute value before applying your logarithm, since that way we can be assured that everything is positive and there's no problem. And actually, it doesn't complicate things all that much to take an absolute value first, because we know ln of the absolute value of x still has an easy derivative that we talked about previously. Let's consider this function, for example. For functions of this form, I've encouraged you in the past to ask yourself whether you're looking at a power function or an exponential function, since we use different formulas for differentiating each of those different types. But in this case, it's actually neither of those, since the function we've been given contains variables in both the base and the exponent. So actually, none of the formulas we currently know are directly applicable here. So in a situation like this, it is necessary to logarithmically differentiate. That's going to have the advantage of turning our exponent into a coefficient, which avoids the problem I just described entirely. But let's get into the specifics. Starting with the function that we've been given, we want to apply a logarithm to both sides. But be cautious. It's actually possible that x to the x represents a negative value, so to be safe, we should apply an absolute value to both sides first. Our logarithm now lets us pull the exponent down, effectively fixing all the problems we had with this function. And with that, we're ready to implicitly differentiate. On the left side, the derivative is 1 over y times the derivative of y using the chain rule. On the right side, we need to use the product rule. So first, x gets differentiated to give us 1. And then ln absolute x gets differentiated to give us 1 over x. Now we can multiply the y over to the right side to get the dy over dx by itself. And I can make a few simplifications to the right side as well, which you can pause and check the simplifications that I've made here if you like. And as a final step, don't forget that y can be expressed in terms of x using the formula given to us in the question. And after doing that, you can present your final answer. In quick summary, there are really two situations where you should think about using logarithmic differentiation. This method is helpful when your function contains a lot of products and quotients. And this method is necessary when your function has a variable raised to another variable. That's all for this topic, so I'll wrap things up here and see you next time.